All right, well, good morning, grade nines. Yeah, listen, I know I've been in contact with some of you already just over email and also on the sort of new group chat that I would like you to use. Listen, if you're watching this video, you're at home for the first day, okay? And what my plan is when you're at school, I'll teach you the lesson in class. When you're at home, okay, I will broadcast a lesson like this. You can watch it. It's not going to be a live lesson. I figure that's logistically too difficult for me to do that. So what I'd like to do is just record these ahead of time, and then I'll post them that morning, like you know, maybe around before I leave for school in the morning. I'll post it, and then you can watch it whenever you want to. Just make sure you take care of it before the next school day, because then we're moving on from there. All right, well, my name is Mr. Flynn, and this is day number 1. I'm going to meet you all on Tuesday morning. Okay, and you're going to meet me in the football field. The other half of the class is meeting me on the football field tomorrow morning, but on Tuesday morning, it'll be your turn. And so you'll see me, I'm the guy with the crazy hair, and you've probably seen me around some of you before, but yeah, anyway, I'm looking forward to getting to know you. I'm glad we're coming back to school. And what I'd like to do now is just get right into it. I don't want to waste too much of your time. And so there's a lot in this lesson. So I'm gonna get to it, and I'll sort of go through everything with OneNote and everything else. But if you're watching this, you should see my OneNote screen right now. You need to be able to access OneNote, and you do that using your school account. And also you need to be able to access Slack, which is our group chat for the class. And what I would like you to do is anytime you have a question for me, I don't want you to send me an email, okay? I would like you to send me a message on Slack. Number one, it's instant. So like I'll get a notification right away. Email's a pain, okay, this way. Sometimes there's 5 or 6 of you that have the same question. And so like if you post it on Slack, we can have a little group chat about it, which is way more efficient for me. And group chats are kind of fun. So already there's like about 1,000 cat pictures on the random channel on our group chat. Yeah, so they can be fun. Just keep it civil, keep it nice to each other, and never post anything inappropriate, because remember, I'm there. This isn't Snapchat, okay? This isn't some of your social media where you're just posting whatever you want. So like there is a teacher there, okay? And so it's okay to post a joke or something like that, but make sure you're posting that in the random channel or something, and maybe I'll make a separate channel for certain things. And we'll keep like the one for the class and important things and for extra help, we'll keep that clear of noise, okay? So anyway, yeah, I'm just gonna go through a couple of things just before I get into the lesson. Number one, you're gonna have a lesson from me every day, whether you have it at school. So that'll be one way of getting a lesson. But you're in cohort B, that's why you're watching this video. So your first lesson is going to be online. So that's this one, okay? But when you come to school on Tuesday, cohort A will get this lesson online, or another lesson actually, because they're going to get this one live tomorrow. And that's how it's going to work. And what happens is, the way it works is, if you get sick, or you know how it is with COVID. I mean, if you have symptoms, you're not supposed to come to school, and you might just have a little scratch in your throat. You might have just a cough or a bit of a headache or whatever it is. And there's so many different possible symptoms. You're not sure if you should come to school. When in doubt, stay home, okay? And you'll just, let's say you're in cohort B, but you're not feeling well on Tuesday. Well, you can just watch the video that cohort A is going to be watching. So, as long as you're well, you're not really that sick or anything. And mostly COVID-19 is like that, right? So like you might have a few symptoms and maybe you have COVID-19. Well, we don't want you to come to school, but there's nothing really preventing you from learning online. Like you're well enough and not really that ill. And in fact, that's by far the largest portion of people who get this virus. They don't really get blown away by it, right? And, let's hope that nobody gets it. But if that happens, or if you have to stay home for any reason, I don't want you to miss like 2 of the live lessons and then fall behind. So you'll just tune in with the other cohort and you can just pick it up online. So I think that way is the best way to do it. And so that's my plan, okay? I might occasionally broadcast a live lesson. I don't know, I'm not really ready to do that right now, but I might try that, but not tomorrow, that's for sure. That's why I'm recording this one on Sunday night. All right, so even if you're doing this online, and I've prepared notes for you on OneNote, you should take your own notes, okay? So you should have a notebook and a binder. You should bring that with you to class, but you should also have it when you're working at home. Okay, so like I wrote that in the letter, but probably many of you didn't really read the letter, so I'm just going over that. If you need a Chromebook or a desktop, Chromebook, we can help you with that. You really do need to have a computer, okay? Everything's gonna be posted on the computer. I am photocopying handouts for you to have at school, but you know, you're not always at school, so you're gonna need a computer to access my online lesson, the notes, and sometimes even other related material that are related to the course, and of course the group chat and everything else. So if you don't have a Chromebook, talk to me, okay? Send me a message. And on the group chat, you can send me a private message, right? Like you can just talk to me. You don't have to talk to everybody. So do that. And I have Chromebooks at school that we can sign out to you that only you will be allowed to use, but you can take it and keep it for the entire school year. We just have to sort of sign it out to you. You're responsible for it, of course. And if you break it, you buy it. That's basically how it works. But yeah, we really need you to have that. And of course, internet access is very important also. So anyway, hopefully that's probably for most of you, it's not a problem. But if it is a problem, let me know, okay? Lunch. When you come to school, of course, when you're at home, this does not apply to you. When you're at school, though, you're going to come and see me on Tuesday. I'll tell you this. You can stay in my classroom. You're going to have to stay together anyway. So let's say you all decide to go to the lunchroom. You have to stay there as a class, okay? Like, you're not going to be able to sit with other friends at all at school. Like, the 14 of you or whatever that are in my cohort B, you have to sit together at lunch all the time, even when you're in the cafeteria, because you're trying to minimize like your cross-contamination with other people, right? So you can stay in my classroom if you want. Okay, so I'm going to make that available to you. You can take your mask off only when you're sitting down and eating. Okay, you have to be socially distanced. And then of course you have to put it back on as soon as you're done. If you get up for any reason to walk around or to go to the bathroom or whatever, you're going to have to put your mask back on whenever you're doing that. Okay, so they're pretty strict. You know, we want to stay at school, right? We don't want there to be an outbreak at the school. So the masks basically have to be worn all the time. Okay, but when you get to school, we'll make these rules more clear to you. And that's it. So that was the letter I first sent home to you. Now I just want to talk about the course for a moment, because you're missing the first lesson. Like normally, you know, I talk about the class because you're going to be with me for 2 months. Normally I'd have you for the whole semester, and you're my homeroom. And normally that's pretty special, but during this pandemic, it's kind of weird. Okay. So anyway, we'll talk more about that later, but let's just talk about this course for a second. It's science class. That's what we do semester 1. You are so fortunate that you have me semester 2 also, but that won't be until after Christmas. Okay, I think you know that because right now I'm your period 1 class, period 2 is in the afternoon. And in the second quad, you're doing period 3 and 4 from semester 1. And then after Christmas, we're going to switch to the second semester courses. You'll have me again in homeroom, okay, from like February and March or whatever, something like that. And then you'll switch and finish the year with your period 3 and 4 courses, whatever those are. Okay, so here's what we're doing in this course. We're going to start with learning about my favorite subject. My favorite subject is talking about astronomy or outer space, okay? I went to university and I studied astrophysics, and I really love this topic, so I hope you'll like it too. I like to start with something I really love, so I hope you'll like it too. How are you going to get marked? This may change. This is how we traditionally do it. This whole thing, like I'm going to circle this whole thing with the RST, I don't think we're going to do that this year, which means your exam will be worth 30%. There will be an exam, okay? If we're still like at school and stuff, there'll be 2 exams. There'll be one for cohort A when they come in, and then there'll be another one for cohort B. It has to be that way. I'll have to make 2 different versions. I might do some of it on the computer in case anyone's sick, and you can do an online exam. And if you're in class, you'll do it online also, but of course, like I'll be supervising it there. So like preferably you'll do it in class. If someone can't be at school, but they're healthy enough to write the exam at home, then we'll figure it out. Okay, there's assignments. In fact, I have an assignment for you today. We're gonna go fast. We only have 2 months to do all that stuff, right? So it's gonna go pretty fast. Labs are kind of interesting. You can't really touch anything, okay? But there may be a way that we can do some of the labs as long, I think you're the only students that are in my classroom, the 2 cohorts. So that means if cohort A does a lab and then there's 24 hours before cohort B does it, then it's considered sterile and you can do it. Like, so certain labs we may be able to do this way, but I think for this year, I'm gonna have to demonstrate most of them. It's fun to see it, but yeah, it's just the way it is, unfortunately. Fortunately for you, you're only in grade 9. Hopefully by the time you get to grade 10, this will be over, okay? So tests and quizzes, yeah, there's gonna be lots of those. We'll have one later this week and we'll talk about that. Yeah, I prefer doing them when I see you. Okay, so what it means is cohort A would probably do it first because they're starting, and then you guys will do it second, okay? I have a website where I track your marks, okay? So you can see your marks anytime. And yeah, it's called Teacheries, so you see it here. Don't worry about it, it's not set up yet. When I have marks for you, I'll enter them in and I'll send you your username and password or whatever. Okay, and you can log into it and check your marks. Now, if you haven't signed up yet, please go on to the group chat. This is how you're gonna send me a message, okay? Email's a pain, and I don't wanna answer your emails. If you can get on the Slack, got a group chat, that would be great because it's a really fantastic way. I've had group chats with my students every year for the past couple of years. It's great, okay? Especially now using Slack because you can have a separate channel for the silly stuff that people wanna post, and then a serious stuff like here's my real question when I get overwhelmed with all these notifications for like a bunch of cat pictures and stuff. So you can just turn on the channel that has to do with extra help. And then if you want to check the other one, you can check that some other time, the silly one, okay? Anyway, we're using OneNote. So here's a link to the OneNote thing. I know that if you go into, this is already in OneNote, but I know I emailed this to you and your parents. So you just click on that and use your student username and password. I know my attempt to use Microsoft Teams didn't work. Forget about that. We're using Slack. That was a group chat anyway. So we're gonna do OneNote for our notes and everything else, and that's it. Cell phones, when you come to class, you can bring your Chromebook or whatever, okay? But cell phone is a distraction. So please leave that in your school bag. You're not gonna get lockers, so you're gonna bring your school bag into my classroom. Just turn off the notifications, put it in your school bag. If your parents wanna talk to you, call you, text you, whatever, tell them to call the school, okay? And let's get those distractions out of the way, okay? Yeah, and that's it. So, keys to a successful year for you, pay attention. So that means like, cell phone policy, like respect it. Participate in the labs. Now, whether I'm demonstrating it for you or whether you're doing it yourself, pay attention, okay, to what you're seeing. Very important. Write notes down, okay? So you should have a notebook ready because I'm about to start your lesson. You should have a notebook ready. You're gonna take little notes about what I'm saying. I'm not gonna write everything down for you. You have the advantage, you can rewind this video and you can take a look at it again or fast forward or whatever, skip to the lesson. This one's gonna be kind of long because it's my introduction to you. But after that, it'll be shorter, just get to the lesson and that's it. You may not be able to attend classes regularly, but do the online. Okay, so if you can't be in class, do the online class. If you're really sick, obviously, okay, that's different. But if you are able-bodied, okay, so if you're like, if you have the sniffles, you're not supposed to come to school, but that doesn't mean you're not sick enough. You're sick enough to not do an online video and get your homework done, right? And same for me. If I have a sore throat and it's a bit unusual, I'm not going to come to school, but I'm going to broadcast my lesson from home, okay? For both cohorts in that case, okay? So you'll have science every day, unless something really bad happens, and the odds of that are quite small actually, okay? So odds are even if you get the virus, you probably won't be that sick going by just the odds. Okay, so I will do whatever I can to get a lesson to you every school day. And your job is to just tune in and follow through with that lesson and do your homework and stuff like that. That's your part. Okay, I love giving extra help to students. So long story short, Slack is for extra help, okay? For asking questions, for whatever, okay, you want to say to me, you can do it on Slack. You can send me a picture of your question, and I can send you a picture of my response, that kind of thing. So please use Slack. And if you're at school and you're in the cohort that's at school, you can talk to me at lunch. Obviously, like I can't like sit next to you, and that's the way we normally do things and sort of go through things. But you know, we can talk one-on-one live, okay, like in person if you're at school, and that's it. Okay, so yeah, please don't hesitate. If you're lost, ask for help. Really important. Okay. All right, so that's my little introduction to you. I'm really looking forward to meeting you in person and seeing your faces. Maybe we'll get a chance to go outside and spread out, and we can actually see your face without the mask, because I won't recognize you otherwise. Okay, but anyway, yeah. So you can ignore the signature here, by the way. You don't have to sign this one. And you cannot use the charging station at the front of the class anymore. So your cell phone has to be in your bag. I understand that you want to carry it with you, but it cannot be just bugging you during class with the notifications and everything, okay? So just put it away during class. In your bag is fine. All right, so let's get to, like I said, my favorite topic in the grade 9 class. My favorite unit is the space unit, and guys, you're gonna love this. I love it, and like I know it's an online lesson. It kind of sucks, but you know, I'll do the best I can here. Okay, I actually took a lot of time to prepare my own notes for you because the textbook's not so good. You won't have a textbook today. You won't need it. You're gonna get your textbook tomorrow when you come to class, and then you'll have it from then on. But for now, you won't need it for today. Okay, so look, due to the accelerated schedule, I have my outline laid out in lessons like this. So there's about 17 lessons in the space unit. Because we do 2 lessons a day, okay, if you do the math, then by the end of next week, we'll be finished the space unit, right? So it's very fast. It's like we're going very fast. So each unit is approximately 2 weeks, right? Approximately 2 weeks. And that includes the tests and everything else. If I give you a test on day number 9, that would be this Friday, okay? And we will have something like that. Now, you're cohort B, so I think I'm seeing A on Monday, Wednesday, and Friday this week, and I'm seeing you on Tuesday and Thursday only. So you would be next week, like maybe next Tuesday or something like that. I can't remember the exact schedule of everyone, but like, you know, we'll do the best we can, but I want you, if at all possible, to write the test in person. And what you'll do is, if you're in cohort B and you're sick on the day of the test, let's say, or can't make it to school, I will give you an online test to write that day, assuming that you're well enough to write it, and you're just staying home as a precaution, okay? So, okay, with all of that in mind, alternatively, I'll just get you to write it when you come in at lunch or something like that. You can just sit by yourself at your spot, and we're going to have one spot. You can sit in my class, and you can just write the test the next time I see you, depending on how you're doing, okay? All right, so there you go. There's a brief outline of the space unit, and you know, this is all in OneNote, okay? And as you can see here, I've prepared the first 3 or 4 lessons here, and we're going to do 2 of them today. We might do 3, just because they kind of all link together with the history. And then what we'll do is, after we've looked at the history of our understanding of space, then what we're going to do is we're going to get into the actual modern, like, astronomy, what we know about space today, okay, in 2020. But it's good to know where these things come from. So this history lesson is really cool. In fact, you know, when you're studying space like this, like, you know, ask yourself this. Right now, you study science, and like, in a science class like ours, if you were, say, alive 500 years ago, you wouldn't be in school. Like, we're middle class. Like, middle class people basically didn't exist. There was working class people, and there were like the rich and the wealthy and the royalty and stuff like that. And so middle class, you would have been not so middle. You would have been poor. You would have been a lower class citizen. Lower class citizens didn't go to school. Now, you might think that that's a good thing, but they didn't know how to read. They didn't know how to write. They didn't know how to do any math or anything like that. And basically, education, knowledge is power, right? Okay. So the rise of literacy among poor people led to the middle class being created, right? And it actually changed our world significantly. 500 years ago, who would you go if you had a question about the world, the universe? Who would you ask? And the answer is not a scientist. They didn't really exist that way back then. You would ask a priest, okay? And the priest would not only be sort of up to par on, say, scriptures and religion, but also about science, okay? And that's the way it was. And in fact, there was a lot of superstition woven into it. Like, astrology was a thing. It was a kind of science back then. That's your horoscope, okay? But these guys that sort of unlocked the mysteries of the universe and understanding about what our solar system is like, that's all started with that. They changed everything. Like, they really set us on a path with the rise of science and not the fall of religion. I shouldn't say that, but just the rise, we call it the age of reason, where we start explaining things in a very different way compared to what they would have done, say, in the Middle Ages. Okay. All right, so let's get started. Lesson number 1. Okay, so you should be able to see all this on your screen. Okay, and I'm going to start by just asking you this question. I'm going to zoom in quite a bit here. Okay, so if you are an ancient person living like 2,000 years ago and you look up at the sky at night, first of all, since there's very little light pollution, you're going to see an amazing view of the night sky. Okay, if you've ever been out in the country and looked up at the sky and how many stars you can see, they're really countless stars. In the city, you can't really appreciate it because we have light pollution here, which means the light drowns out, light from the city lights drowns out some of the light that you would see otherwise in the night sky. Okay. Anyway, they didn't have telescopes. So 2,000 years ago, there was no such thing as a telescope. They couldn't manufacture glass or anything like that. So what you had were naked eye observations of the sky. In other words, just what your eyes, your little eyeballs in your head, whatever you can see when you look up, that's all you saw, okay? But you'd be surprised at how much you can see with just your eyes, okay? So first of all, what kind of celestial, which means out there in the heavens, celestial, okay, classifications of objects, what kind of objects do you see just with your eyes when you look up at night in the night sky? Okay. Now, if you're in my class, I would let you answer this, by raising your hand and, contributing. But I have these notes already here. So let's get the obvious out of the way. First, the big guy, okay? The brightest thing out there, the sun. Okay, so the sun is the brightest light in the sky, probably the most important light in the sky. It's responsible for life on Earth, right? I mean, it didn't create life on Earth, but what it does is it provides the energy of life on Earth. So plants, through photosynthesis, create food energy, and that is the basis of energy in the food chain. You are powered by the sun. All life is, okay, pretty much on this planet. There are a few microorganisms that are a little weird that don't do it, but most life on this planet is sun powered, okay? So the sun, very important. The ancient people knew this. They knew how important the sun was. It's the brightest thing out there, okay? All right, next we have the next brightest light in the sky. It's a lot dimmer, okay, especially here where it's only this is a waxing crescent moon, we call it. We'll talk about the phases of the moon later. But the moon, when it's especially a full disk that you see in the sky, is the second brightest light. Not responsible for life on this planet, the energy of life or anything like that. It's just not bright enough. Okay, but yeah, that's the other thing you can see with your naked eye. Of course, there are stars. Okay, now here in this area, let's see if I can use the color red. Here in this area here, you can see sort of cloudy formation, those are really densely packed stars. That's the Milky Way galaxy, right? Now, of course, ancient people did not know about galaxies, guys. So remember, we're talking 2,000 years ago, but they did see these stars. Absolutely. In fact, they saw them quite clearly. Now, if you go out in a country where it's very dark, you can see the Milky Way with your eyes, okay, with your naked eye. So stars. Now, what they did, especially the ancient Greeks and Romans, was they grouped the brighter stars, especially, into patterns that we call constellations. This one is called the Big Dipper, but it's actually part of a bigger constellation called Ursa Major, which is the Great Bear, okay? So the Big Dipper, you see it here, forms a little pattern, like a little dipper that you dip into a soup or something like that, and you put the soup in here, right? So that's why we call it the Big Dipper. These stars here actually point towards another star, it's off the picture here, called the North Star. It's up here. So that's how you can find the North Star if you want to navigate somewhere, by starlight, which ancient cultures did as well. Now, there's one other thing that the ancient civilizations knew about, and it's kind of a cool thing. They knew about planets, okay? Now, here's the thing. If I were to take you, if we go outside at night and we take the whole class and we go outside, we socially distance, of course, you look up at the night sky and I say, all right, I want you to find me Saturn. Now, you can see Saturn with the naked eye. In fact, you can see Mercury, Venus, Saturn, Mars, and Jupiter. Venus, by the way, the brightest one. But my question for you is, if you didn't know any better, could you tell that these were not the same as stars? Because they actually look like stars, okay? They seem totally indistinguishable from regular stars in the sky. So how'd they know, right? Well, I have an answer for you, and I'm going to try doing this. I've got a little app I wanted to show you called Star Chart. It's a free app if you care to install it on your phone or something, you want to try it. But, it's just like the sky forms a map, okay? The stars in the background, the ancient people, let's say the English translation is stars, they have stars, but planets are different. But here's the thing. Most people don't realize they're different because you just take a look and you just see this point of light in the sky. You don't know it's Jupiter, okay? In order for you to know that there's something different about that point of light, you can't just look at it for a few minutes. You have to watch it not over an entire night or anything like that. It won't seem to be any different than the background stars. You have to look at it for several months, okay? Go out every clear night and find Jupiter. And what you'll find is something is different about that little star-like object. There's something different about it. And in fact, the other planets too. Now you might be wondering where some of the other planets are here. Uranus, Neptune, Pluto doesn't count, right? Pluto's a dwarf planet, not big enough. Pluto's smaller than our moon, right? It's not really big enough to be considered a planet. There's certain criteria a planet has to meet to be called a planet. And mostly for Pluto, it's because of it's so small, right? That's the problem. All right, so why don't we see any of those other planets here? It's because you can't see them with the naked eye. These are the only planets that you can see with the naked eye, these 5, okay? So Mercury, Venus, Mars, Saturn, Jupiter. And by the way, did the ancient people think Earth was a planet? The answer to that question is absolutely not. Earth is not a planet, okay? Earth, okay, remember, I'm not talking about today. I'm talking about back then. Why isn't Earth a planet? Well, Earth, we're standing on this world. Earth was the world, right? Like it was the physical realm. Think of it like if you've seen the Avengers and stuff, think of Asgard. Like Asgard is out there in the heavens, okay? Planet is a celestial object out there in the heavens. They thought they were spiritual beings. Like the Roman word for Jupiter is Zeus, right? That's a Greek. They thought these were like gods out there in the heavens. Earth is a world. These guys are like gods floating out there, spiritual beings, okay, out there in heaven. Okay, and that's literally how they thought about it. And so, of course, Earth is not like that. Earth is this physical realm. Like we were the only world in the universe. There were no other worlds. That doesn't make sense. There was the heavens and there was the earth. And that's how they saw it because they didn't know any better, right? In fact, we didn't learn that Earth was a planet for 1,500 years, okay? At least after people started studying the heavens like this. So thousands of years basically went by where they thought of it that way before we realized Earth was a planet too. So planets, how can you tell the difference? All right, let me see if I can show you this app. I'm going to do my best. There's a close-up of the planet Saturn, as you might know. Could you see rings around Saturn with your naked eye? The answer to that question is no. You can't see rings around Saturn with your naked eye. You need telescopes for that. All right. Well, here we have a little star chart. Okay. So this is a virtualization, but the thing about this is that it actually portrays the heavens accurately. So this is what you see in the night sky. Of course, you don't see the centaur with the bow and arrow, the Sagittarius constellation. You don't see it, the horse itself, of course. It's just a series of stars that they've joined together to form these constellations. Okay, so that is in Roman and Greek mythology, right? That's why these things look like Roman and Greek myths. Okay, you might notice that as you're going around. All right, if you want to look at Sagittarius for a moment, you'll see that there's a couple of interesting objects there. We have Jupiter and Saturn, right? And we have Pluto. You can't see Pluto with the naked eye. Okay, but on this app, they label it. Now, if we cross the horizon, we cannot see this here. Here we see Mercury. And if you look, the sun has set, like right now it's 9:43 at night. Okay, so the sun is dipped below the horizon, but it's still there. Okay, and the ancient civilizations knew that the sun wasn't gone when it disappeared below the horizon, it was circling the earth. That's what they thought. Okay, now, if you notice this dotted line, okay, this dotted line is called the ecliptic. Now, here's the deal. What the ancient civilizations knew, okay, so here is Leo, constellation Leo. You can see it right here, this pattern that's drawn out. If I get the, sort of get it in the right spot, there's the lion. Okay, so there's Leo the lion. And if you look at this, Leo is right along that dotted line. Okay, also Virgo. Virgo is this angel-like statue here. The sun is actually between right now. It's between Leo and Virgo, okay? So what's the deal with this dotted line? Well, the sun, here's what the ancient people figured out. It's a really amazing story, okay? By carefully observing the night sky and the constellations, what they realized were, like, for example, at this time of year, you cannot ever see Virgo and Leo. You can only see them during the winter. And what they realized was, the reason for that is the sun gradually moves along the dotted line through all of these constellations. So right now it's approaching Virgo. And after Virgo, it's going to enter, I think that's Libra. After Libra, there's Scorpio, then there's Sagittarius. In December, the sun will be just approaching Sagittarius. And if you're born in December, right, that's why your sign would be Sagittarius, because that's where the sun is every year in December. It moves along this dotted line, okay? And here's Capricorn. I don't know what that one is, the twins or whatever that is. That's Pisces there, the fish. Okay, so what happens is that dotted line, the sun moves across that map. Now, if I keep going far enough, I will get back to where the sun was. So what's the sun doing? Well, it's moving across the map. Now, it does it very gradually. In fact, it takes 1 year for the sun to make it all the way through all 12 zodiac constellations. And those are like the ones that we just mentioned, Leo, Virgo, and so on. Okay, Sagittarius, et cetera, et cetera. So the sun makes its way across the map, passing through those 12, we call them zodiac constellations, along this dotted line that's called the ecliptic, okay? And what happens is, if you were paying attention as I was scrolling, you'll see that the planets are close to the dotted line too. There's Jupiter, Saturn, Pluto. Okay, if I just follow the dotted line, oh, there's Neptune. Now remember, you couldn't see Neptune back then. There's Uranus, you can't see that one either, not without a telescope. Okay, Venus, there's Venus right there. It's just passing through Scorpio. Okay, and here we are back to the sun, and there's Mercury. Okay, Mercury is right in the middle of Virgo right now. Okay, so here's the deal. You see why those 12 constellations are special, right? Like the Big Dipper, Ursa Major, Ursa Minor, the Big and Little Dipper, Orion. They're not on the dotted line, those other constellations. So those 12 are special because the sun moves through it. Now, to prove to you that the sun moves through it, I can use this app to fast forward time, okay? So here is the sun. I've put my focus on it. Now it's going to get a little weird. I'm going to fast forward and speed up time. And hopefully, all right, let me go back to normal. Let's see if I can do that again. There. So here the days are passing by very rapidly, okay? And what's happening is we're seeing the course of the sun, okay, as it moves across the dotted line, across our map, through all the zodiac constellations, one by one, okay? So if you pay attention to the dates at the bottom, every December, it approaches Sagittarius. Now here, we're coming up on the summer again. So like when it gets to August, you'll notice Leo, okay? So there's July, there's August, see there's Leo, and then right after that is Virgo in September and so on. Okay, now I'm gonna stop this. So you see what the sun does? Through the course of a year, it plots its way, moves across the map, okay? The stars in the background never move. They're always in the same positions, okay? The planets though, and if you notice, the planets were also moving across the map, okay? And you see, that's how you can tell Venus is different. You have to watch it for a long time. Watch it for several months. It moves across the map. The background stars don't move. They stay in their patterns in their constellations, right? And you see, the Greek word for wandering is planet. And that's where the word planet comes from. All right, so let's get back to one note. Okay, so planets, you can tell a planet is a planet because it moves across the map. Okay, just like the sun does, and the moon does too, by the way. It takes the moon 27 days to move across the map. It takes the sun 365 days to move across the map. And the other planets, it varies from planet to planet. Some of them take more than a human lifetime. Jupiter takes more than a human lifetime to move across the map, but it moves, okay? Very slowly, but it moves, okay? All right, so take a look. Here, I wanted to show you this. So number one, I just defined all these things for you. So they're here in the notes. Constellations are groups of stars that ancient civilizations have assigned shapes, okay? Zodiac constellations are special because they lie along a line called the ecliptic. And if you look at the definition of the ecliptic, it's the sun's path across the map of constellations. So it takes 1 year for the sun to move through all 12 of those zodiac constellations. And if you're wondering, I've listed them for you here. You should recognize these names if you know anything about astrology. Now, please don't tell your parents I'm telling you astrology is true. I'm not. I'm just telling you where it comes from, okay? So look, there's the constellations Aries, Taurus, Gemini, Cancer, Leo, Virgo, Libra, Scorpio, Sagittarius, Capricorn, Aquarius, and Pisces. My sign is Sagittarius. That means I was born while the sun was approaching the Sagittarius constellation. If you were born in today, your sign would be Virgo because the sun is about to enter Virgo, okay? So you see, that's how it works. Okay, these 12 constellations are special because they're the ones that the sun keeps passing through year after year after year after year. So you just trace out that line on a map, okay, and that's called the ecliptic. That is the sun's path across the map of constellations. The Big Dipper is not on the line, so it's not as special, okay? Okay, so I already explained what astrological signs are, and for example, August 22 to September 22 is Virgo because the sun, well, it approaches Virgo during that time. It kind of like by the time it gets to September 22nd, the sun is kind of on Virgo's shoulder. And I show you a picture of that here. Like here, take a look. This angel is Virgo. You can see here, this line here is the ecliptic, right? Like that is the ecliptic. Okay, now the sun is at the top. Okay, now this is on August 22nd. So that was a few weeks ago. Okay, that's where the sun was. Now, when I made these notes, it was September 5th. Okay, so that was like 10 days ago or so when I started making these notes. So we can see that the sun has moved from approximately here, now it is down here. So in the course of a couple of weeks, the sun has made some progress. Now, if you look at Mercury, Mercury was here, now it's down here. So Mercury has traveled. Let me use a different color maybe for Mercury. So here's Mercury here. Now Mercury's down here. So Mercury has traveled from approximately here over to there in that same amount of time. So you see how Mercury's different, right? It's not just another star in the background. It moves, okay? It moves across the map. Now, if you just watch it on one night, you won't see it moving. Like it'll just hold its position, okay? So it moves very gradually across the map, taking many months, okay? In this case, a couple of weeks, but the Mercury actually moves at a greater rate compared to the sun. Okay, Mercury will traverse the whole map like 4 or 5 times a year, okay? Venus will do it a couple times a year. Mars does it once every 2 years, okay? So it depends on the planet. The sun does it once a year, okay? Sun's not a planet though, okay? So like the sun's very special. Now, by the time you get to September 22nd, look where the sun is. Actually, I should go back to red. The sun is now on the shoulder of Virgo, right there, okay? So it's moved all the way down to there in the course of about a month, okay? Now, next year on September 22nd, sorry, 2021, hopefully by the time we have a vaccine and we can not wear masks at school anymore when you're in grade 10, this is where the sun will be. Now look at these two. They look like the same picture. They're not the same picture. Like what I'm saying is I did not just copy and paste the same picture to play a trick on you, okay? I didn't do that. You can actually tell just by where these words are located that my clip is slightly different. It actually is the next year, but it doesn't matter. Any September 22nd on any year, that's where the sun is, okay? So it repeats its course every year through these 12 constellations, right? All right, so there you go. How do you tell a planet from a star? Well, we already did this. So here, take a look at Mars. So here, let's use a highlighter. Whoops, no, that looks terrible, sorry. Let me go back to red. There's Mars right there. Okay, now that is on July 20th. Now Mars moves quite a bit slower than the sun, so we have to sort of give it a little more time. So I went back to July 20th, just backwards in time in the app, and that's where Mars was. Now look, it's right around the constellation of Pisces, okay? Now, Mars, Uranus, and Neptune, like, by the way, all 3 planets are moving, but Uranus and Neptune will move quite slowly across this. You might not notice much difference for them. But Mars, like it takes many years for, I think it takes something like 11 years for Uranus to go all the way around the chart. Okay, so it's extremely slow progress. Mars once every 2 years, so it's much faster, 26 months approximately. So look where Mars is here. Now that is a couple of months later. So Mars has clearly moved, okay? It moved from there to there basically over the course of a couple of months. So Mars moves. So in Greek, the word planets means wanderer. So those 5 little dots are special. Those 5 little star-like objects in the sky are not stars. They move through the constellations. They're special, like only the sun does that and the moon, okay? And the planets, they move through the constellations. So sun and moon are different classification of objects. They're so much bigger and brighter. Planet looks like a little star and it's like wandering through the constellations, right? All right, so that's it. Now, by the way, every once in a while, a planet will do something that the sun and moon never do. And let me show you here. Okay, so take a look at this. Hopefully you can see this. This is the planet Mars being tracked for several months in 2003. And look, it did this weird thing, okay, where it does a little backwards motion. That backward motion is called retrograde motion, where it goes backwards along its path. The sun never does this. It just keeps going forward all the time. So let me explain that to you here. Retrograde motion, okay, the planet normally goes that way. Okay, so in other words, in this picture, the planet is normally moving across the map from right to left, but every once in a while, it goes the other way. That's called retrograde motion. For Mars, it happens once every 26 months, okay, on schedule. Okay, now the other planets, Jupiter, it's about once a year. Saturn is about once a year also. Same with Uranus and Neptune. All the outer planets are about once a year. But Mars, it's about once every 2 years, okay? Venus, it happens several times a year, except you can't see Venus when it retrogrades. I'll explain why later. The ancient people didn't think that Mercury and Venus retrograde, okay? And it's because you can't see it. Like they do retrograde. In fact, they retrograde quite often. But whenever they do it, they're invisible to us, okay? Which I'll explain. They can't see them in the night sky. All right, so that's retrograde motion. This is crucial, guys. Retrograde motion. Why do planets move backwards like this? Now, remember, you're not thinking like a modern person in 2020. Try to put yourself in the shoes of somebody like 2,000 years ago who knows nothing about space, who just goes out there and watches Mars for a couple of years and said, it just went backwards. Why is that? Okay. All right. So in order for me to get to the next part, we're going to talk about some ancient Greek philosophers. One of them is named is Ptolemy. In fact, that's the only one we're going to talk about. There's also Aristotle. He did some work with space, but Ptolemy's probably the most famous one. Okay, now before we get there, okay, so like Ptolemy's going to put this all together for you. He's going to make a little model. Now the model's not right. Okay, I'm going to put that out right away. Remember, it's 2,000 years ago, so they didn't have you and I enjoy the benefit of thousands of years of history on this and information that they lacked, okay? Remember, they didn't even have telescopes, just going by looking up at the sky. Okay, first of all, where is Earth in the universe according to the ancient people? Well, it's in the center of the universe. So geocentrism, geo means Earth, okay? And geocentrism is the belief that the Earth is the center of the universe. Now, you might be thinking, okay, that ancient people were just so full of themselves that they had to put themselves in the center of the universe. Like, it's just like some little kid or something, he thinks he's the center of the universe, everything revolves around him. That's sort of the expression that we use, right, for a spoiled kid. That's not it, okay? What does the sun do every day, okay? Well, it rises in the east and sets in the west, and that's what the sun does every day, okay? Does it seem to be circling us if you didn't know any better? Doesn't it seem to be circling us? Like this planet or Earth that I'm sitting on doesn't seem to be moving, but the sun seems to move. It seems to be circling us. It's kind of obvious, right? And what if I were to tell you that every star in the sky actually does the same thing as the sun does? It rises in the east and sets in the west. And the moon does the same thing. So wouldn't you conclude that it appears, at least just from appearances, that everything is circling us and we're at the center of it all? Well, that's how it looks, okay? Now, they didn't know they were on a ball that's spinning. So if you were just to stand in the center of a room and spin around, from your point of view, it might look like the room is circling you, okay? But in fact, you're on this world that's spinning. They didn't know the world was spinning. It doesn't seem like it's spinning, right? You don't feel it spinning. Okay, so anyway, look, to prove this to you, if you've ever watched, this is a picture of what's called star trails. So here, like if you leave your shutter open on your camera for like 90 minutes, you'll see that stars do seem to be circling us. Okay, so take a look. I'm gonna lower I don't want any volume on this video. Okay, I don't know how well this video is gonna come through in this, but I'm just gonna sort of cut to the chase. All right, so here you can see, this is a time-lapse photography, okay? So obviously you don't see stars this way. They're showing the trails that they sort of leave behind on the camera frame, okay? This is really cool. So there's what we see in time-lapse, and then if we let the stars leave trails behind, then they look like this. Now what's really cool is in the center of this picture, right here, is a star that doesn't seem to be circling us. That is the one called Polaris, and that's the North Star. We'll talk about why that one doesn't move. So here you can see Polaris right there in the middle. but all the other stars seem to be circling around the heavens, right? With us right underneath the center of it, okay? So they rise in the east, okay? In this case, like rising on this side and setting on this side, okay? And that's what they do. So why do we think Earth is the center? Common sense. Just look, we seem to be in the center, right? It's absolutely true. I put this in though. Einstein once said, common sense tells us the Earth is flat. Okay. In other words, Einstein didn't have much patience for people who argued based on common sense. So if they said, hey, listen, like, you know, obviously climate change, humans couldn't possibly change Earth's climate. Why? That's common sense. Yeah, no, sometimes common sense is nonsense. And that's what Einstein's trying to say here. He's not defending flat Earth. Okay. All right. So here's a picture of Ptolemy. Look when he was alive. So about 100 years following the death of Jesus, okay, approximately, there's this guy named Ptolemy. He lived to a ripe old age of 70. Back then, that was an old man because they didn't have medical care like we have now. So no photographs, of course, it was too long ago, but 2,000 years ago, roughly. Okay, just a little bit less than 2,000 years. We had this guy. And he had an explanation for how the world looked. This was a flat Earth, probably. I know it looks round, but it was a flat Earth. The continents looked very different. Of course, there was no North America back then because they had not discovered it yet in Europe. So there was only Asia, Africa, and so on. Okay, maybe Australia down there. But this was a flat Earth, and there was like beyond the edges of that disk. So Earth was basically a disk, okay? And around that disk, here we see the Zodiac Constellations. Do you see that? There's Sagittarius, Scorpio, and so on, okay? And they were laid out along the ecliptic, which formed a ring around the Earth. The sun moves around that ring, okay? So if you want to find the sun, you would find it right there. And what it's doing is circling around the disk, okay? And that's what the sun does. In fact, everything does, okay? Everything, even the stars in the background, everything's circling around the Earth. Just like we saw the star trails. So this is Ptolemy's model of the universe. It's a geocentric model, probably a flat Earth model, and it looks kind of around there. Definitely, I'm pretty sure they believed in a flat Earth back then. So yeah, you might look at this and go, well, this is not right. But there's a few interesting things to notice about it. And to show you, I'm going to show you maybe something that's a little more clear. Here's how they figured it looked, okay? First, they knew the moon was the closest thing. Why? Because the moon sometimes blocks the sun. So they had to be closer, right? That's during an eclipse. So eclipses are not that rare. So they would have seen eclipses. One human lifetime, you usually see a couple of eclipses, okay, or at least partial eclipses. So you would know that the moon has to be between the Earth and the sun. Now, what I think is really cool is Mercury and Venus they have before they have the sun, okay? So it's true that Mercury does transit in front of the sun, okay? And so does Venus. Venus transits in front of the sun too. But there's no way they could have seen that, not back then. In fact, it took centuries before anyone actually saw the transit of Venus and Mercury. Transit means when it passes between the sun and the Earth. These planets are so small compared to the sun, they just look like little specks, okay, moving across the sun's surface. And the sun is so bright that you could never see them, especially with a naked eye. You can't even look at it. So anyway, but somehow they knew that Mercury and Venus transited in front. I'm not sure how. I've never been able to get an answer to that question. And they were right about that, actually. Mercury does pass between us and the sun, and so does Venus. And here's the thing. That's when Mercury retrogrades. Same with Venus. It only retrogrades when it's between us and the sun. And that's why you don't see it. That's why it never happens. Because it's happening during daylight where the sky is blue and you don't see Mercury and Venus. So they do retrograde. That means going backwards. But they only do it when you can't see them, okay? Now, the ancient people didn't think they retrograded at all. All right, so here's Jupiter. So what's Jupiter doing here? Here it's retrograding. Now, it only does that once a year, okay? So Jupiter will make its way around, and then once a year, it will retrograde. Pretty much does it in the same constellation all the time. Mars will do the same thing, except it does it once every 2 years. Okay, Saturn is around once a year. And they didn't have any other planets on the list because they couldn't see Neptune and Uranus and Pluto and stuff like that. Like I said, Pluto doesn't count. All right, so that is the ancient view of the universe, guys. And that's it. Okay, there's really nothing else to say about it. Fast forward like 1,500 years, and then things start getting really interesting. Okay, so 1,500 years later, and this is starting lesson 2 now. And like, if you want to take a break and just break this video up into segments, I'm talking for a long time because I don't want to lose my train of thought. So I'm not going to make separate videos. It's getting complicated. I'm just going to make one really long video. And you can like pause it and break it up and just remember your spot and pause it and come back and watch it later. Okay, so here, things start getting really cool during the time of the Renaissance. Okay, so look, this guy named Ptolemy, he was alive just after the death of Christ, like basically 1 generation later. Okay, so in those days, what happened was the early Christians went to Greece, okay, where Ptolemy was. And they incorporated Greek philosophy into Christianity. Okay, so when the church went to Greece and Rome, the philosophy about space got incorporated into church doctrine. In other words, geocentrism and the Ptolemaic model got incorporated into Christianity back then. Now, it's not mentioned in the Bible. Nowhere in the Bible does it say Earth is in the center. That doesn't mention the planets. The Bible isn't really about any of that. Okay, I mean, imagine the Bible's a much older document. Imagine mentioning Mars and Mercury and stuff to ancient people who never even knew they were there. Okay, so yeah. Anyway, unfortunately, it got incorporated into church doctrine that Earth was in the center of the universe, which seems really arcane to us now. But that was just common sense, right? And it became like sort of an important spot, like God made Earth in the middle of everything, right? Anyway, after the fall of the Roman Empire, there was a period called the Middle Ages. So this lasted for about 1,000 years. Now, sometimes we call it the Dark Ages, but so that's not really politically correct to say that anymore. Dark because like a lot of the documents of that time were burned, okay, and so on. So like we're not really sure. There's probably a lot of good stuff that we'll never know about back then. That was during the Middle Ages. Now, Renaissance, around 1300 to around 1600, so a period of about 300 years. They invented a printing press, and that meant you were able to take a document like the Bible. It was handwritten, everything was, and copy it. Okay. Now, what people did was they translated it into other languages, and so for the first time, the average person, like libraries were built with books and copies of books, right? And they distributed all this information all over the world, right? It was like the first sort of like slow version of the web, right? Or the internet. Like you have this huge collection of information that was making its way out into the world. And the average person, this is important, the average person learned how to read, okay? So it wasn't just the priests and the royalty that learned how to read. Other people during the time of the Renaissance started to learn how to read, okay? And maybe the first schools were sort of built around this time where they started teaching people to read, okay? So it's a very important period in our history. It had a massive effect on philosophy, art, architecture, music, science, okay? And, there was a very tumultuous time because once people learn how to read, they start becoming educated and they're like, wait a second, the priest has been telling us that the earth is the center of the universe. And like, now that I know how to read and I'm starting to study it myself, I don't know, and there were new ideas being entertained probably for the first time. Now, the church back then, like I said, I'm not, don't get me wrong. This is a period in church history that had a lot of unfortunate things about it, but the church, not the church as Jesus wanted it to be, let's put it that way, but the church had become a political entity. They had their own police, they had their own army. They bear no resemblance, okay, to the church that exists today. Okay, and now some of this stuff was unfortunate and definitely not in line with Christianity, okay? But, it is what it is. Like that was the status of the church back then. They were a political force. In fact, a very important political force, especially in Western Europe. Okay. They had all the power. They held all the cards, right? If you wanted to get to heaven, it was through the church that you got to heaven. They could forgive your sins. You go to a priest, you get forgiveness, then you can get to heaven, and they sometimes would hold that over someone, right? So anyway, along comes, and imagine that as your backdrop, okay? And remember that Earth being the center of the universe is like a tenet of Christianity. They incorporated it in. It's unfortunate too, because it wasn't in the original scripture, but because the early Christians went to Greece and they shared some of those Greek philosophies, they incorporated it into the doctrine of the church. Along comes Copernicus, who's a Christian. All these guys, all the guys I'm about to talk about, they're all part of the Roman Catholic Church, okay? So just to get that clear, a lot of them were going to be priests, educated men, and so on, okay? And mostly men, because it was patriarchal, sorry, girls, but the world back then was not as inclusive, even less inclusive than for today. We're trying to fix all that, but like back then it was terrible, really, okay? But these guys, were trying to crack open some of these doctrines that the church was teaching. So along comes this guy named Copernicus, and he was alive from 1473 to 1543, right? So right in the middle of the Renaissance period. Educated man, okay, who studied. And what he did, okay, was he revived, probably someone in the Middle Ages came up with this before he did, but he believed that you could explain retrograde motion, okay? So here, the apparent movement of the planets and the sun would be better explained if the sun was the center of the universe or the solar system and the planets orbited in perfect circles. No little weird backwards movement, because you don't need backwards movement to explain retrograde motion if the Earth is orbiting the sun, okay? So the Earth is not the stationary object, but it's orbiting the sun too. Now, the sun is called Helios. I don't know if that's Greek or Roman or whatever it is. So we call this notion that the sun is the center heliocentrism, just like geo means Earth, so geocentrism. Heliocentrism means sun at the center. Okay, now here is a picture of his model. Okay, now if you look at this is his original script. Here, Sol is the sun. That is, Sol is the name of our star. Okay, in the center. There's Mercury. There's Venus. Terra, of course, is Earth. Now the moon is orbiting around Earth. You got that right too. Okay. Then there's Mars. This one's Jupiter. They call it Jobus. Okay, and Saturnus is Saturn, of course. And then these are the background stars. And the background stars are still sort of spinning around like they did in the Ptolemaic model. Okay. So he actually got the order of the planets correct. Okay, but how did he explain retrograde motion? Well, that's easy. Watch what happens. Okay. How do you get backwards movement? So watch. When Earth passes Mars, Mars will appear to move backwards. Now, if we're at school, we could like go to the track outside, and like if someone's running faster around the track than you are, when they pass you, they will appear to be moving in a certain direction. But when they're on the other side of the track compared to you, they're moving in the opposite direction. So that's what's happening with Mars. Mars retrogrades when Earth passes it, okay, in its orbit. And that was Galileo, or it's not Galileo, I'm sorry. That was Copernicus's idea of how you could explain retrograde motion with Earth being in orbit. Now, if Mercury or Venus pass Earth, same thing, they would retrograde, but you can't see those retrograde. Jupiter once a year, Saturn once a year. As Earth passes those planets, they would retrograde also. Okay, right on like clockwork. Okay, Mars, like I said, every 26 months. Now, what happened to Copernicus? Well, sad story, really. He was afraid to release this document, his book that he wrote about it, called like the motion of the celestial orbs. Okay, he was afraid to release it for fear of scorn, basically. Okay, he was afraid that because it was, everyone just felt it was such a obvious truth that the Earth is the center of the universe, and it was established church doctrine. He didn't want that kind of scorn in his life. So he sat on the theory in the book for 20 years. And his friends and colleagues really pushed him to release it, but he didn't want it. He was too afraid of the scorn. So what he did was he eventually released it. And 2 months later, he died. Okay. Now, when he first released it, the book was highly mathematical. So the church didn't know what to do with it at first. Once they figured out what it was trying to say, they eventually condemned it as heretical, which means you're going against the teaching of the church. And they banned it several decades after his death. Okay. Yeah. So that was kind of a sad story for him. He did release the book before he died, but unfortunately, he died like 2 months after releasing the theory. And that's the story of Copernicus, guys. So he's the first one that's recognized with a written down theory with the sun at the center, okay? And everything moving in circles. All right, we're almost through this history, guys. I know it's a very long lesson. Like I said, break it up with break. You want to take a break right now? Take a break, pause it, and come back, okay? And it's way more fun to get this live because I can show you certain things, okay, that I can't really do here. I've got the notes, but anyway. All right, let's talk about Tycho Brahe. So Tycho Brahe was an astronomer and an inventor, okay, and he built a device called a sextant. Now I've got a sort of sketch of it here. It's a big thing. It looks like it's a big protractor or something. Now what you do is you point it typically at a celestial object. Now what's it for? Well, it's for measuring very precise angles. Okay, so here, this is in your book, by the way. It's in a homework question. Let's say I want to tell you how to find Jupiter tonight. Okay, well, how will I tell you? How will you know where to look in the sky? Okay, now I could tell you based on a constellation. I could say, well, just look for the Big Dipper and, look sort of down and to the left, but that's a bit difficult that way, right? What if I were to give you 2 numbers, and those 2 numbers will tell you exactly where the planet is? Okay, well, I can do that. The 2 numbers I would give you are a number called azimuth, and the other one is elevation. Now, your book calls elevation altitude, but it means the same thing, okay? So let's say here's our point of light in the sky. Call it a planet, call it a star, call it the sun. It could be the moon, whatever it is, okay? It doesn't matter, okay? Anything, any object that's in the sky, you can do this. Now, north, let's do azimuth first. You would need a magnetic compass, which they did have. That's an ancient invention. A compass is thousands of years old. So you make a compass, north, south, east, west compass. That's what I mean. Now, 0 on the compass, 0 degrees means north, okay? 90 degrees would mean east. South would be 180 degrees. So let's say right now the moon is located at 180 degrees from, like, standing where you are, 180 degrees. So which way would you point if you wanted to see the moon? Well, you would point south. You get it? Let's say the moon was east right now, okay? Then I would say it's 90 degrees. Now, let's say somewhere between east and south. Well, then I would say, let's say 105 degrees and so on. So that would be a compass reading. So azimuth is measured on a magnetic compass, okay? North, south, east, west. Now, the sextant is not made for measuring that. That's what compasses are for. The sextant is made for measuring altitude. So here, this sextant is designed to get a very precise measurement of altitude or elevation. So in other words, I tell you to point your face south, so you turn 180 degrees from north, now you're facing south. Then I have to tell you, the second number I have to give you is the elevation. So where is Jupiter in the sky? Okay, well, let's say I tell you it is at 75.6 degrees of elevation. So now what you do is you take your sextant, you point it 75.6 degrees up from the horizon. Now you're pointing right at Jupiter. You get it? So this celestial object up here, sorry for my writing, it's hard to write on this thing. So that celestial object is what you're pointing at. If I give you these 2 numbers, there's no guesswork. You can tell exactly where it is. You could find whatever you're looking for, okay? So this device was designed to make extremely precise measurements of altitude, okay? Like right down to fractions of a degree. Like you could say, 45.767 degrees. And that device, 500 years ago, could do that, okay? So that's Tycho Brahe. He invented that. Okay, now otherwise he didn't really have much contributions. Okay, but his apprentice, a guy named Johann Kepler with a funky beard here, this guy was amazing. Okay, so he worked for Tycho Brahe, especially during the last 2 years of Tycho Brahe's life. But he was a brilliant mathematician. That was not Tycho Brahe's thing. Like, probably he was good at it, but Kepler was on another level altogether. Okay, now what the two of them did over the course of a couple of years was they collected a whole bunch of really precise angular measurements of altitude and azimuth of all the planets over the course of 2 years. Okay, and so they had this set of data. Okay, and what Kepler decided to do, he was also a Catholic. Okay, he wanted to prove that the church was right, that the Earth really was the center, and he's going to use data to do it. Right. So in other words, he's going to make some measurements. He's going to prove with the measurements that the Earth is the center. Okay. Now, let's say there's this method that he came up with called parallax. So how do you tell how far away the moon is, okay, from Earth? Well, it's simple. You take two people, this guy and this guy. You give them each a sextant, okay? And you say, all right, let's go out tonight at exactly 10 p.m., okay, and measure the elevation of the moon and the azimuth and elevation of the moon. Except I'm going to be in Toronto, you're going to be in Ottawa. Okay, so we're like hundreds of kilometers apart, and we need to know exactly how far apart we are. So in other words, we need to know how much this distance is. Now we're going to measure these two angles here and here. Now, if we collect these measurements and we know exactly how far apart our sextants are, then we'll be able to, using trigonometry, or that you'll learn in shortly in your math class and stuff, you can figure out how far away the distance is to the moon, okay? And that is called parallax, when you use this method of triangulation to determine distance. Now, in the future that, that Kepler could not realize was that we ended up eventually figuring out the distance between the Earth and the Sun using his method of parallax. We needed better instruments and a massive, it was a massive undertaking that they did in the late 1700s, and they were able to find the Earth-Sun distance. They had these sextants all over the world, just in case it was cloudy. And imagine doing that before the telephone, before technology, communicating with people, like by, by courier, by basically guys going around on horseback. Okay. Anyway, they got it done and they figured out the distance. Okay. Now Kepler's data, unfortunately for him, he wanted to prove the church was right. He did exactly the opposite. He proved the church was totally wrong. But he had irrefutable proof now. He had data to back him up. Okay. So here's what he came up with. Planets. Copernicus was right that planets circle the sun, but they don't do it in orbits, like or in circular orbits. They do it in elliptical orbits, which is like a flattened out sort of football-like circle where one axis of the circle is stretched out. Okay, we call it the semi-major axis. And the sun is at what's called the focus of the ellipse. Okay, in class I could explain what a focus is, but I'll just leave it. Okay, there's two focal points. There's actually nothing at this focal point. And here's a planet, and the planet just goes around like that, right? Orbiting around over and over and over, right? This is what Earth does year after year after year. In fact, 1 year is one lap around the sun. So if you're 13 or 14, maybe you're 13 now, I guess. So some of you are 13 turning 14, I guess. So for you 13-year-olds, you've done 13 laps, right, around the sun. And maybe you're on lap number 14 now, whatever it is. And yeah, so when did Kepler figure all this out? Like 500 laps ago, right? That's a year is one lap. Okay, so law number 2 is best seen using an animation. So I'm going to show you this. You can see all this in OneNote on your own, by the way. Okay, law number 2 is a little weird. If you draw a line from a planet to the sun, that line is called a radial arm. And what it does is it sweeps out equal areas in equal times, okay? So all of these pieces of pie that you're seeing here being swept out as the planet goes around the sun, they're all the same size, the same area, that is. So if you're trying to share the ellipse equally, if we gave everyone a blue piece, one of these blue or gray pieces, they'd all be the same size, so no one could fight over it, right? So that's Kepler's second law. Now, in order for that to happen, when the planet gets closer to the sun, it has to speed up, okay? And it does that. It speeds up. When it gets closer, watch. See, it's far away, it's going slow. And then when it gets close enough, it speeds up, okay? So planets, that's what they do. That's law number one. Okay, I don't know what this YouTube video is. Okay, anyway, that's law number one. Or law number two, pardon me. Law number three, okay? Each planet has its own orbital radius. So in other words, the distance that the planet is from the sun is different for every planet, right? Mercury's closest, and you know, like this is in millions of kilometers. Now, I should point out to you that Kepler didn't have these precise numbers, but he had ratios, okay? So if Earth was 1, like Mercury's like 0.38 or something, right? So he knew the ratios based on the time it took them to go around once. Now, these are in millions of kilometers. So these are millions of kilometers. And this is how many days, Earth days, are in a year, okay? So notice Earth, 365.2. That's 1 year for us. The 0.2 is why we have leap years, okay? Mars takes about twice as long as that. Jupiter, look at Jupiter, geez. It's like more than 10 years, right? And Saturn, really slow, okay? Saturn is like 30 years, you know, like approximately 30 years to go around once. And Uranus and Neptune, even slower, like, okay, very slow. Not 30 years, I'm sorry. 10 years would be 10, yeah, 30 years. Okay, anyway, now there's a mathematical pattern here. Now, I don't want to waste your time because you're watching this online. You're probably really bored by now. Okay, so I'm going to show it to you. If you take these numbers, and for each one, these numbers here, this is R. And for the length of the year, we're going to call that T, like it's a period of time. Now, what Kepler noticed was if you take R cubed and divide it by T squared, every time you get 25. So you can try that for these numbers. Try it for Mercury, try it for Venus, try it for Earth. And what you'll find is that every single time, I'm sorry, for some reason, my son was playing these videos. Oh yeah, never mind this, I'm going to show you that later. All right, let's get back to this. So you get this every single time, the number 25. So try it for Venus. This is Venus's R, this is its T, time for 1 year. Try it, you get 25. Now, it's important to note, Kepler didn't know why this is happening. In fact, all three laws, he didn't know why. That's just what they're doing. Like, in other words, he just had the numbers, right? He's just crunching the numbers, saying these are the patterns. They move in elliptical orbits. They seem to go faster when they're closer, right? And law number 3 is that they have this weird relationship between the distance and the length of a year. There's a mathematical pattern to it. He's a mathematician, so he saw the pattern. He had years to work this out, though. Don't feel bad if you can't see it in 2 seconds. You know, if I gave you a few years to work it out, maybe you'd come up with this, right? So, you know, remember, this was his job. This is what he did. So these are like, you know, when we say a law in science, we don't mean like laws in court, which, like, you know, you could break the law. He just means that this is what they're always doing, right? So that is a law in physics. We're just telling you how things always are. Does that make sense? So in other words, if I say that if I drop the pen, it falls because of gravity, it just always does when you drop it. Okay, so that's the law of gravity. It's not obviously something that can be broken if it just always happens. Okay, so he's just saying the planets always do this, right? So they're always doing these 3 things. Okay, now along comes this guy named Galileo. Okay, now he's a big proponent of Heliocentrism, the sun being at the center, big proponent of Copernicus. The church did not like Galileo very much. Anyway, he didn't invent the telescope, let me make that clear, but he invented a really good telescope. So he took the existing telescopes, which are kind of crappy. He made one that for the first time had a magnification factor of about 30 times. The old ones are maybe 2 or 3 times. This is 30 times, it was a lot better. Pointed it at Jupiter, okay? And when you point the telescope at Jupiter, you're going to see some things that you can't see with the naked eye. So the invention of telescopes really important, okay? Pointing it at celestial objects, really important, these really great telescopes, okay? Now, this is what Jupiter looks like to the naked eye. It just looks like a little point in the sky. Here, let me show you this. Okay, I'm going to go back to my app. Hopefully it still works. I may not be able to get it to come back. Okay, never mind. So look, here's Jupiter to the naked eye. You see the little dot. Oh, there it is. Okay. Yeah, when you look at it through Galileo's telescope, it looked like this. So for the first time, you could see this weird coloration on Jupiter. No longer is it just a sort of nondescript point of light. It has texture to it. It has these little lines across it. Okay. Now, what are these other things that they've labeled here? Io, Europa, Callisto, and Ganymede. Well, what Galileo did was he watched them for a few weeks, and they actually are orbiting around Jupiter, okay? And so Galileo goes to the church guys and he goes, listen, not only are you wrong, okay, about the Earth being the center of the universe, the sun is the center, but Jupiter is the center of its own little system, and Earth only has one little guy going around us, the moon. But Jupiter has 4 of those guys. In fact, we found more than 60 now. There's like 67 moons, but most of them you can't see like this. You need a much better telescope. We need to go there with a probe, right? Which we've done. So anyway, Galileo sees the moons of Jupiter. Now we call them the Galilean satellites, Io, Europa, Callisto, and Ganymede. Some of the most fascinating objects in our solar system, okay? Anyway, Galilean satellites, very important. Galileo also saw phases of Venus, like the moon has phases, like crescent moon and full moon and so on. Well, Venus has phases too, okay? And for the first time, he saw phases of Venus. That was important also. All right, so that's the contribution of Galileo. So Galileo invented the telescope, saw the moons of Jupiter, basically supported all Copernicus and Kepler, okay? And there was really only one thing, guys, left in the history, so I'm almost done. And we can't stop here. We have to talk about one more guy. And this guy was probably put it all together really nicely. So what I'm going to tell you is, like, in the past, if you were wondering why someone got sick, like let's say someone got cancer 500 years ago. Well, they didn't really know much about cancer back then, but if you ask like the neighbors, like, why did that guy get sick? And they say, well, you know, because he sinned against God and God made him sick. And unfortunately, and this is a really unfortunate philosophy, okay? Yeah, they believed like in supernatural explanations for a lot of things. So for example, there's a drought or the wildfires in California. Well, that's because they have a lot of sin out there in California, right? Now, I'm not saying that's the truth. Don't get me wrong. Okay, so let's put it this way. That's not what I believe, okay? That's not what the Catholic Church believes today. So let's be clear. But back then, that was the general feeling, okay? So in other words, most people explained unexplainable things using supernatural causes, like a lightning strike was Zeus, right? That kind of thing. That's not how we explain things today, okay? So we don't explain it that way. I can't think of anything we explain that way today. Okay, so what happened is this supernatural, it was Isaac Newton that set us on the right path away from supernatural explanations, okay, and sort of like, yeah, like, you know, like it was almost, It's almost based on fortunes, right? Like you had good fortune and bad fortune, you know, like so this sort of supernatural explanation for things, whether the gods were happy or not. But Newton, he changed all that. Now, not all overnight. Okay, so let's get that straight. Newton was a Catholic too, a devout Catholic actually. He wrote more books about Christianity than he did about science. But his most important work was the science. Okay, so look, heavens were like Asgard, up there in space. Those weren't, remember, like those weren't worlds. Like Jupiter wasn't a world. Mars wasn't a place you could go and land on to the ancient people. It was a spiritual being. It's like Hermes. Okay. So if that's the case, if that heavens up above us is this supernatural realm, then really what can we learn about it when we're studying science? And the answer, or we're studying, like trying to understand why Mars does what it does. Well, we can't really answer those questions. Mars is a spiritual being. Who knows why he does what he does? We don't know what the rules are out there. Okay. So along comes Newton. And you see, here on Earth, the physical realm was governed by what we call natural laws. Okay. So when Newton said that, like, you know, an apple falls from the tree because of a force of gravity, that wasn't a stunning revelation. That was common knowledge. Okay. Maybe he named it gravity. Okay. But he had a very different way of thinking of it, but still it was considered natural. Like it wasn't God that makes the apple fall, right? It just falls because it's natural for it to fall. Just like when if you throw something or whatever and it comes back down and hits the earth, they just do that because it's natural, right? All right, now in ancient Greece, the material world, our world, governed by natural laws, was considered evil, chaotic, transient. Death, pain, and suffering were here, and so on, disease, right? And that's how the ancient Greeks thought of it. And unfortunately, that got incorporated a little bit into Christianity also, okay? That was not in the original Bible where God creates the earth and it was good. That's what it says in Genesis, right? Not that it was bad, it was good, okay? But anyway, let's get back to Newton. So Newton was studying motion of objects here on Earth, okay? And he came up with 3 laws, not like Kepler's laws, which are only for planets. Newton's laws are for everything, okay? So inertia. Inertia is the tendency of an object to do what it's already doing. So let's say, for example, you have a smartphone. It's sitting on the table in front of you, okay? You take your hand off it. Now, I think you'd all be scared out of your mind if for some reason the smartphone floated up by itself and flew across the room, right? And smashed into the wall or something like that, right? And you think your parents have like telekinetic powers. See, things don't do that because of inertia. An object at rest just tends to stay at rest. We know it's natural for the phone just to sit there as long as nothing's disturbing it, right? Now, if you take it and pick it up with your hand, well, now you're disturbing it, okay? Now, the other side of this law is that an object in motion tends also to stay in motion. So for example, if you roll a ball along the floor, it just won't suddenly stop for no reason. So in other words, let's say a ball is rolling, marble is rolling on the floor, and we're suddenly to turn to the left for no reason, right? Doesn't hit anything, doesn't, of course it wouldn't do that because an object in motion tends to stay in motion and it tends to keep doing what it's already doing. So if it's moving, let's say forward across the floor, it doesn't stop, slow down, turn left or right for no reason, unless, you know, something were to redirect it. So that's where law number 2 comes in. When an unbalanced force, a push or a pull, acts on an object, then it will change its motion. It'll change its direction or speed or both, okay? So there's a relationship between force, which is a push or a pull, okay, and a change in speed, direction, or both. So now if you hit your phone, it'll move. It'll change its direction and speed and so on. That's because you exerted an unbalanced force on it, okay? Now, action and reaction is the 3rd law. So for every action, there's an equal and opposite reaction. We don't need to talk much about that one. Let's put it this way. If you're leaning against a wall, you're touching the wall, but it's also touching you, okay? And so forces come in pairs like that, but that's not important for us right now in grade 9. More on that in grade 12, in grade 11 physics, okay? So here was his genius moment, okay? There's a 4th law. Now, when he was studying the motion of the planets and Kepler's data, he realized, Newton realized, I'm just reading the sentence to you, that these these natural laws can explain the motion of the planets too, if you add one more thing to them. And that one more thing is gravity, okay? So objects tend to move in straight lines, but planets are moving in these elliptical orbits for one reason. And here's was his genius moment. It was the same reason the apple fell from the tree, right? So he connected the apple falling from the tree to the Mars orbiting the sun. Why does Mars orbit the sun, spiral around it? Why didn't it just move off in a straight line? Well, the only explanation was there must be a force that's pulling Mars towards the sun, keeping it from moving away, okay? Keeping it in orbit. And that force was the same one that caused the apple to fall from the tree. Now, that is not an obvious connection, but Newton was like one of the most unparalleled geniuses in the world. Like, he'd be the equivalent of Albert Einstein in today's world. Just an amazing genius. He invented, you'll be studying so much about Newton in school, not only if you take physics class, but if you take calculus in grade 12, it's a math class. Newton invented that. Okay, like, that's how smart he was. He invented it when he's like 5 years older than you. Okay, like, he's basically 20 years old, doing this, 6 years older than you maybe. Okay, anyway, so gravity, any object with mass attracts all other objects with mass. Okay, so this amazing revelation from him. So what he realized was that these things orbiting the sun are not spiritual beings at all. They're just like inanimate objects, like a rock. Okay, you throw a rock, it follows this curved path, it comes back to the earth because of gravity. That's what Mars is doing around the sun. It's like this projectile is just moving around the sun because of gravity, right? So objects aren't moving out there for supernatural reasons. They're moving out there because of natural reasons, right? So this was the first time that we didn't think of it as the heavens and the earth anymore, but it was one physical universe governed by natural laws. And now we explain everything with natural laws, right? Why did the lightning strike? Well, we don't invoke Zeus anymore. Now we say, well, it's because of these conditions and this buildup of charge and so on. We do electricity in the future, okay, in this chorus, but that's it. And now, 300 years later, this started off the age of reason. And now, because of the age of reason, you are lucky enough to be, like I wrote here, to be in my class and be really bored by this video, okay, me telling you about it. So anyway, guys, that's my little history for you. Like, you see how important it is, right? Like, all these guys studying just why planets go around the sun and what the model of the universe is. And we go from this very supernatural explanation at the very beginning, you know, or this astrology and everything else, okay, and now we come all the way to, you know, a few hundred years ago in the late 1600s, early 1700s, Isaac Newton, and he comes up with this brilliant sort of idea that the whole universe is just one place, not like the realm of Asgard or the heavens, right? And then another realm here on Earth, but actually just one realm, one physical universe with the same physical laws. We call them universal laws that don't just work here on this planet, but they also work out in outer space, okay? Now, Newton didn't know how gravity works. Like, he was able to put numbers to it, but he knew there was a force there, force of attraction. Why that force is there, believe it or not, we still don't know the answer. You could win a Nobel Prize today if you could answer that question, how gravity is able to do what it does, but it does. And yeah, so anyway, look, I want to show you this one more time. So here's Kepler's second law. What happens when a planet gets closer? Of course, it moves faster, okay? And so Kepler did not have an explanation for this, but Newton has an explanation, okay? So watch, figure skaters do this too. Now this move is called a scratch spin. I'm not a figure skater, but I am amazed by this move. So if you're a figure skater and you can do this, wow, okay, like, I am impressed. I skate, I play hockey and stuff like this. I am so impressed. I don't know how people do this, but anyway, watch. How they do it without getting dizzy and just falling down, I guess it takes a lot of practice. So watch this skater. And I cannot believe how quickly she spins there. I cannot believe it. I can't get over it. And then just comes out of it like it's nothing. Anyway, just if that video wasn't clear in this, just look up scratch spin okay, on YouTube. And it is amazing. So how does Newton explain that? Well, it's the same thing. When she brings her leg in, okay, when she brings her leg in, like watch, her leg is out. When she brings it in closer to her body, it's like the planet getting closer to the sun. What happens? She spins faster. Same thing with the sun. Newton would call this, he came up with other laws after the first four. So this one's called the law of conservation of angular momentum. It's just natural. So planets do it too, okay? In fact, when our sun dies, the sun spins very quickly, believe it or not. When it dies, it's going to become a lot smaller. And when that happens, it is going to spin like mad fast, like unbelievably fast. And those are called neutron stars, okay? And I'll explain that later, okay? But anyway, there you go. So that's the history, guys. Now I have a little bit of homework for you. I'm sorry this is a really long video. I get it. It's like 2 lessons. And like I said, you know, you don't want to, I'm going to give my own students in class breaks during all this. So if you sat through this whole video, congratulations. If you listened to me the entire time, you are like a god of listening or something. I don't know. I don't think I could do it. But anyway, I hope you broke it up and took breaks and then came back and made it more manageable. I do have some homework for you. To get to the homework, what you would do is in each of your folders, like let's say your name is like Ada. Okay, I'm sorry if I'm saying your name wrong, Ada. Okay, Ada Petreja. Okay, or Petreja. Okay, but anyway, sorry about that. I know you will correct me when we get there. So if you look in your homework section, I put some homework in there for you, not just for you, okay, for all the students. So can you, like, from memory, okay, now you can do this how you want. If you want to read my notes, the notes are pretty complete. You don't have to listen to me at all if you want to just read them, okay? But complete the following chart. Okay, so what is the brightest light in the heavens? I think I know the answer. Do you know the answer? Okay, and if you guessed the sun, you would be right. So if I were you, I would write the sun in there. Now, let's say you don't have a tablet like mine and you don't want to write like that. What you can do is you can actually, let's see if this works. Okay, sorry, no, you can't do it there. So what you do is you pick a blank spot and go the sun like this, and then just take that and drag it. I'm sorry if it's a little imprecise. You drag it in there and there you go. You got it? Okay, so you fill in the blanks. So you can use this tool how you want. You can type in the answers. Please don't scratch it in with your fingers. Like I get students that do this and then they start writing on it. I can't even do that with my finger. Or with the mouse, where you tap on this and then you start going like this. Let's see if I can do this. No, it's not going to let me. No, it won't let me because it knows I have a pen. Okay. But please don't draw the answer, the sun, in this horrible writing with your finger and the mouse pad, and the trackpad. Don't do it. You're going to lose marks, okay? So I expect it to be neat. So type it in. Here you can type all this in. Just type it in an outside box and then fill it in. Now, what's the second brightest light in the sky? Well, that's the moon, of course. What's the ecliptic? Do you remember the ecliptic? Very important, okay? Zodiac constellations, what are those? What does wanderer mean? It's a planet. It's a planet, okay? So anyway, fill in the chart. There's a second exit card. This is about the lesson 2, like the Renaissance guys. So, who proposed heliocentrism? If you guessed Copernicus, you would be correct. What did Tycho Brahe do? Okay. Which scientist came up with the 3 laws of planetary motion, and what are those laws? Okay. Who came up with 4 laws that we just did this? You should get this. But anyway, get the idea. Now there's some textbook homework as well. Now here, what I did is, because you don't have a textbook yet, you're going to get it on Tuesday. I put a copy of the textbook page in here for you just with the questions. So name 3 different objects you can see in the night sky. So there's question 1. You have to do 1 to 10. If you're in the city, sun, moon, the night sky, pardon me. So you can see the moon, you can see planets, okay? And you can see the background stars. Does that make sense? All right, what is meant by light pollution? That is when you're in the city, you get ambient light from city lights that obscure the starlight. So we call that light pollution. It's not like real pollution, but that's what it is. Okay, what is the name of the apparent annual path the sun, moon, and planets follow across the sky? That is the ecliptic. Okay. How does Earth rotation affect your view of the stars and constellations in the night sky? It makes them seem to circle the Earth, right? Earth's revolution is, okay, rotation is day and night. Does that make sense? That makes the sun rise and the sun set every day. Revolution is going around the sun once. Okay, so why is, for example, Mars, like, you know, Mars is moving around the system, but Earth is moving too. Okay, so our perspective of where Mars is on the background stars depends on where we are in our orbit, right? So it will shift the position of where the sun appears to be, right? For example, is based on us revolving around the sun. All right, what is this? You should know. It's retrograde motion. So this is taken over the course of a few months, say the position of planet Venus, or not Venus, Mars over the course of several months when it retrogrades, okay? So you can answer these questions. I've done most of them for you. I'm going to give you a chance to do that. Oh, a star that is directly overhead, what is its altitude? It'd be 90 degrees. We call it the zenith when it's straight above your head. Yeah, so I'll let you work that out, okay? So these are pretty straightforward, these questions. All right, so guys, this video is long enough, and I'm just going to go back to if you want to find these notes, what you do is you click on the space tab, okay? And the first 3 lessons are there for you. Don't forget the exit cards, okay, which are here like this. Oh, I should maybe erase what I did. I did erase it, yeah, okay. So, and look in your own homework tab and you can fill in the answers there. I do check the homework. So please do it. Okay, do the homework, please. And if you want to go through these notes again, you can go through them on your own. The notes are pretty complete. Like, I actually worked really hard on that for you. Okay, that was for your benefit since you're staying at home. I normally wouldn't do it like this. Okay, so guys, that's it for me for now. I will see you on Tuesday morning, and I apologize that this one's so long. The next one will not be as long as this, partly because it's the first day and partly because there's so much history to cover. All right, so you can bring your questions to me on Tuesday. I look forward to meeting you, and we'll see you soon.